Take it away, Bill.
Yeah, thanks, Tom. Yeah, so I volunteered to lead the discussion on this really because I think it's a very interesting topic, and there's a lot to chew on here and a lot of problems that we as a community have to solve. And I really just look forward to hearing some of y'all's thoughts about them. So maybe I'll just say what kind of the flow is. I'm going to give a few minutes just kind of recapping some of the challenges that I think that we're facing for using any of these near-term quantum technologies to learn something about chemistry. But the meat of this, I would really like us to break up into groups and to try to imagine that we had solved some of these challenges. You know, picture yourself in a year or 5 years or 10 years, and you're explaining like how you overcame some of the obstacles I'll introduce, and what might that look like? You know, what kinds of features would an approach to these problems have? Is there anything we can rule out as just like totally crazy? I think that's a helpful perspective to take. And so I would love it if folks kind of come from that angle. And then we'll talk for about 30 minutes in these smaller groups. And if you would nominate sort of at least one person from each of the groups to report back on anything that you touch on that you think other people would be interested in, that would be great, because we'll take the last 15 minutes to come back together as a big group. And so, yeah, please feel free to jump in if you have any questions, even along the way, but let's get as fast as we can to that breakout group style discussion. But before we do that, let's just kind of frame what the problem is. And so what are some of the challenges for quantum chemistry using these near-term NISQ devices? And maybe a better starting point even is what do we mean by quantum chemistry? Oftentimes we focus on this electronic structure problem where we have a Hamiltonian that's hopefully familiar to everybody here or familiar to most of y'all. And this Hamiltonian, it encodes various approximations about the physics of the problems. We pick a finite basis set, we discretize it. We imagine that we have some molecule where we've pinned the nuclei in space, and we're just asking about the electronic configurations. And typically we're interested in the ground state properties or the ground state energy. And this can be an input to a lot of other things that we might do in order to understand the properties, or like the structure of some chemical system. So oftentimes we talk about this problem, and we like in classical and quantum computing to use variational approaches to this problem, where we define an ansatz, some parameterized wave function, and we try to minimize the energy. So that's one approach, which is probably the most well-known of these near-term quantum algorithms for chemistry, but there are also many other ways to go about it. But I think it's also worth mentioning here that there's actually a lot of different problems in quantum chemistry. We don't have to just focus on this second quantized ground state problem. There are many places where folks are interested in calculating other properties of a chemical system, its behavior, the way it interacts with like external degrees of freedom, light matter interactions. And there's also places where the Hamiltonian that we wrote here doesn't really capture all of the physics. Perhaps we're interested in a regime where we couple to nuclear degrees of freedom, and we can't just talk about the electrons and sort of then have the nuclei fixed in space. So I just wanted to point this out, and I don't think I have to belabor it, but we could mean a lot of different things by quantum chemistry, and if any of them come up in the discussions, that would be wonderful. Okay, so we have quantum chemistry, and then we have these NISQ or near-term devices. And for the purposes of our discussion, and I think in general, we really mean a big range of things. Sort of any quantum device, quantum computer that's powerful enough to be interesting, but it's not trivially simulable. And that puts some lower bounds on the size of the device and the error rates. If we can easily simulate it on our cell phones, we don't necessarily learn anything about chemistry. But there's also devices that are large enough where we can't do this, but we can't afford all of the machinery of quantum error correction that lets us do kind of effectively have a textbook quantum computer where we don't have to think about many of the issues that might come up. So everything in between those two extremes is on the table for this discussion. That might mean that we have lots of imperfect qubits. It could be 50, it could be 10,000, it could be 500,000. And I think there'll be a lot of regimes in the middle there where we might be able to come up with some interesting ideas. And it also means that we have non-zero error rates. So if we focus, say, on 2-qubit gates, which are kind of the building blocks of many of these quantum algorithms that we're interested in, it could be an error rate of 10 to the minus 2 or 10 to the minus 3. But let yourself imagine, what if we had a much smaller but still non-zero error rate? If there's something that feels interesting in that direction, it would be great to talk about that too. And furthermore, this NISQ, this near-term quantum technology, let's let it cover sort of a wide range of things, not just a digital quantum computer, which is maybe the focus of this workshop, but there's really interesting work going on in quantum simulation with analog systems, or even quantum sensing technologies. So if there are places where sort of those other kinds of approaches might be useful for chemistry, or we might learn something from trying to apply them to chemistry, that's on the table as well. Okay, so we're really interested in a wide range of things for this quantum chemistry and for NISQ. And what are a couple of the largest challenges that I think it would be nice to chew on in these breakout groups? Well, the first one, I'll just summarize it with the word fidelity, but probably the best way to understand what I mean is just to imagine a very simple model of errors. Let's say that we have a quantum algorithm. It's built of m quantum gates, and every quantum gate has some error rate p. So of course, the probability of not having any errors after we run m of these gates is exponentially suppressed in m. And this is going to put a real limit on what we can do if we need the output of our quantum computer to sort of exactly reproduce what we would have gotten in the absence of errors. And I don't need to tell this to anyone who's tried to run experiments on these things that this makes it really challenging to get meaningful information out. And so, what can we do given the fact that this is a feature of the NISQ era? And this is really a problem because, or it could be a problem anyway, because even small calculations on systems that are quite small from a classical quantum chemistry perspective, say tens of qubits, might be tens of spin orbitals or spatial orbitals. We could easily run up hundreds or thousands of gates if we're trying to put together even a pretty short algorithm, a pretty short circuit. And just to put a concrete number out there, the estimated fidelity of the beyond classical computations from Google's 2019 work was about 0.2%. And those were circuits that were, a linear depth circuit. So only, a modest number of gates on something like 50 qubits. And these are the kind of numbers we're going to have to deal with if we want to do something useful for quantum chemistry in the NISQ era. And furthermore, classical techniques are actually very good. We can push exponentially scaling approaches quite far. And if approximations are okay, we can do amazing things, really. So we have a lot of competition, I would say. And then the other kind of big issue that I think is worth keeping in mind and asking if we can think about ways to address it is this issue of the measurement precision. And depending on what we're doing for our calculation, we might require a lot of precision. So this threshold of chemical accuracy could mean errors that are 1 part in 1,000 or less if we're thinking about the units of the Hamiltonian. And sometimes properties that we would like to reconstruct from our calculations are very sensitive to those, and those energies that we might get out or some other observable. And that's why we're so sensitive to those errors. So that on the one hand, we need a lot of precision, but on the other hand, we know that we're pretty fundamentally limited to this 1/epsilon² scaling. If we want some precision epsilon, we just have to make a lot of measurements because each measurement is some random variable, sample from a random variable. And so this is amplified, of course, when we have to decompose a complicated operator into a bunch of simple pieces and measure each of those. And maybe I won't dwell on the different examples, but it's worth keeping in mind that oftentimes we don't just want to measure one state, one observable for one state. We want to make even more measurements. We might want to measure the gradient of some parameterized wave function with respect to the parameters so that we can find the minimum energy of something. Or we might need to measure a bunch of related quantities, the matrix elements of some operator. And so this, this can add up really fast, and anything we can do to reduce the precision that we're asking for, or to sort of reduce the variance of these measurements could be really wonderful. So I think a lot of the challenges we face that many of y'all have addressed more specifically kind of fit into these two categories, but hopefully that's a useful framing. And so, we have these kind of broad challenges, but let's sit down for the next half an hour and think about what would it look like if we had solved them. So, for example, I brought up this issue of fidelity. Well, one reasonable response to that might be, look, we need to do something where we don't need the perfect ideal state. We can actually tolerate a state with very low fidelity, as long as it has like some kind of reasonable type of error. That, as an example, but there could be other responses. So if we had overcome these challenges of the precision and the fidelity, and gotten something useful, either learned something useful about chemistry or about our quantum computing technology, what would that look like? And anything that comes up and is alive for your small group, I think, is worth pursuing. But it might be helpful to have some additional questions here, and so I've put a few on this slide. And I think with that, unless folks have any questions, I'd like to break up into groups and chew on some of this and see like what might be a way around some of these obstacles that I highlighted.
Thanks, Bill. So I'm going to split everyone up into groups now. I've assigned into groups of about 5, 6 or 7. I think so. I think the main thing is we've got the 5 seed questions here. Maybe we can break this. Bill, do you want to break this down to 2? I think we only got 4 groups, so I think maybe if you can choose 2, then we'll make sure that one of them gets that like they kind of get focused on at least one, like one group will answer one question.
Yeah, I mean, I think that those kind of second and third questions people might find them because they're sort of pretty concrete. If we have output of some BQE calculation, how do we know we can trust it? And then what are the advantages we might have for doing a variational calculation on a near-term device versus like some classical techniques? But also, I think if folks have ideas about what kind of constraints there might be on a useful application of near-term quantum computing to chemistry that lie outside of these, it would be great to bring those up as well.
Right, I'm going to hit the button on the groups then, and I'll come around most of the groups just to check in. I'd like to invite people to when you get into your group to like pick someone to report back, have some discussion, and I might time these to say we'll do the first one for 15 minutes just to just to see how see how this goes and to break it up a little bit. All right, I'll see you all later.
Thanks, Tom.
So you should all be able to go out to the breakout rooms now. I think, Bill, you and I don't think, if you close your slide, I can assign you one of the breakout groups. I think I might use you to balance out some of the
that would be great, and you'll keep an eye on them to see how many folks are joining. And okay, great. I'll exit the slides here.
Okay, cool.
And maybe, one more thing, Tom, if you maybe broadcast to everyone kind of what one of those seed questions is, once we're in the groups, it could be helpful.
Okay, I'll do that.
Oh, I lost the invitation, I think, to the room.
Oh, hang on. I'm trying to get you out right now. How do I?
Sure.
Oh, I click edit rooms. Give me a second. I'll be there. I'll be there. All right. Oh, hey, Alice. Let me drop you in here, maybe. All right. I'm gonna drop you in this one, and I'm gonna drop this in group 1. All right. See you in a second.
Cool.
Oh shit. All right, maybe I'll just jump into here then. All right. Hi, everyone. I hope that stimulated some discussion. I see we've got now 10 people here in the call, and I guess we've got a few people in breakout rooms. Let's see. Yaroslav and Sasha. Okay. Also, I see that Bill's back. That's good. That's a start.
Yeah.
Okay,
Yeah. It seems like folks are filtering back.
Yeah, indeed. I guess we've got a bit of a we've had a bit of drop off, but I guess maybe that's to be expected with these things. I have a question actually for Nick. While we've got the big group, maybe you can answer. If I imagine doing a large quantum chemistry calculation on like, if I imagine like preparing just some set of strongly correlated states, and suppose I want to just use my quantum computer to prepare strongly correlated states and measure their 2 RDMs, because like this gives me a set of of pure or 2 RDMs that I know are definitively positive. And so then I can get kind of on the other side of the positive cone than what I get from using these convex optimization techniques with 2 RDMs. How close would I have to be to like the set of how pure would my state actually have to be in order to get some benefit out of what you could just get classically?
That's a tough question because I think the classical competition is very stiff. They are always, for variational algorithms, they're always pure. You're always positive when you're drawing from a quantum computer, really. I mean, thermal state is a positive operator, right? So you always get a positive RDM. The only way you wouldn't is sampling error. So sample some more. So I don't know. I'd say probably never, but
probably never. But sorry, my question was like, when do you think a quantum computer would like? When do you think that the RDM that I produce from a quantum computer would be useful, say, as feed into a classical computer?
So that is, I think, a little different. If you need a correlated RDM for the beginning of a calculation, then that could be the case. You might want to do that. But then I would ask, why not just run like a small MCSEF calculation or small active space calculation and seed your classical routine that needs a correlated, like if you have one of these root finding techniques, like I guess Mazziotti calls it ACSC or Garnett's canonical transform or Steve's canonical transform I mentioned before, it needs to be seeded with a state to start with. And so it finds a root that's close to that approximately. And so starting close to something you care about is important, and maybe a quantum computer be helpful there. But again, I don't know, competition's stiff.
So I guess that was...
Now that we... Oh, I didn't mean to interrupt.
No, Bill, I was passing it back to you. You're the one running.
Oh, great. Yeah, I guess now that we're back from our really chunk of discussion, does anyone have stuff that came up that they'd want to share? It could be incomplete ideas. In fact, those are like super welcome, but just anything interesting that your group touched on. To just feel free to unmute yourself and jump in.
I guess I'll start. I mean, I was with Bill, Luke Fisher, and Vic de Jong, and that was like a tough competition on chemist people that know a lot of stuff compared to me. But we looked at the question of how to compare VQ results when we can actually run true VQEs. And one of the discussions we're having is what to run against a quantum computing calculation via VQE when we cannot have the exact solution. And they come up with like spectroscopy experiments, real spectroscopy experiments, where we could measure optical transitions or something like this. One other question was like, I think an easy target that we should look for in the future is to just have like beating classical predictions, ad initio classical predictions, saying, here's my VQE run, it's better than the best known method for this problem, as far as we know. And that would be, I guess that would be the easy first target to tackle. Then some dynamical properties that you can measure by attaching heavy metals, like that was Luke's recommendation, that some experiments that are done where by measuring also spectroscopy experiments with, but you measure dynamical properties of heavy metals. That's apparently it's much more difficult. And one other proposition that came up with was like try to compare a digital quantum computation via VQE with some analog computation in some Rydberg atoms or some lattice atoms, where you run the VQE, you get some result, and then you go to your favorite experimentalist like Michal Luhin or some Brad Blatter in Innsbruck and tell them, look, now run the same experiment or the same molecule on your lattice experiment and try to verify each other in a kind of fashion. That would be and also a nice way to kind of verify VQEs. And then another thing, there was this proposition it could be very neat, which is like accept by prediction. We run a VQE or we run a near-term experiment. Of some model, we make a prediction of this model, and then somebody goes ahead and builds this, like for instance, in a photocatalysis experiment or in absorbing a photon, predict that some material would do better, go test this material on the lab. If it does better than the known method, it's a way of verifying that a quantum computer has done something meaningful. And well, there is a lot of open questions in how to use the resources doing a lot of qubits and low depth that you have to run for near term, and how to kind of optimize this trade-off in VQ experiments. And yeah, we didn't have more time to discuss up to that point.
Thank you. Does anyone else want to share some of the things that came up in that group?
We were in group 4, and maybe less in detail. That was Oliver, Peter, Tom, and myself. So my background is in density functional theory. And so if I look back 50 years, there's an eerie similarity to the 1970s and 1980s in quantum chemistry to what quantum chemistry on quantum computers currently looks like. The accepted feeling that CI will get us through everything, and then in the end it was just, Javier said, what's the measuring gauge here? It was really the beryllium dimer, right? The beryllium dimer was predicted to be stable with good vibrational frequencies, and first of all lousy binding energies, but later on good binding energies. And that convinced the community that this was useful density functional theory. So what would useful quantum chemistry with quantum computers really look like? Where is the beryllium-2 dimer for this community? And I'm not an expert in quantum computing at all. I've worked with Tom a little bit. We've done the Hellman-Feynman theorem for quantum computers. We talked about that in a very nice paper. But what is it that would get us there? And then we were thinking of things like starting with VQE, but what is the diffusion Monte Carlo or Green's function Monte Carlo analogous process that could get us to the real solution? And we didn't have the answers, but maybe those were interesting questions that you experts, if somebody comes up with a solution to my question, then he's probably sitting here, right? What would it be? I'm asking you.
Cool, thank you.
And maybe Luke will disagree about DFT and the beryllium dimer, but
yeah, maybe let me respond to that. So a beryllium dimer, in my opinion, it's more a copper cluster thing that a copper cluster that solved that. But but DFT proved useful. For a lot of other cases. So your general perspective, I can agree with, of course. Maybe something because these heavy elements. So here in the field that people are working, it's very easy to do predictions. The only problem is they don't get measured. People are actually predicting properties, say, of a dimer of element 112. But or even the phase that these elements would have. But if you would make it, they would be so radioactive. You have a lot of things that are not in your model. So that's a bit a problem. You want to make a prediction, but also something that can be accurately measured. and I think that is hard. I mean, in reality, we always measure a much more complex system. So small molecules in isolation, of course, there's a lot of measurements out there, but I mean, then you're not predicting. I mean, then you can still beat the classical methods in precision, perhaps. Maybe that's where we should go for it.
Great, thank you.
Maybe I can talk for my group. So yeah, we had a discussion mostly with Alexander and Nick, and yeah, so we addressed the question of, well, can we expect anything from NISC beyond what we can do classically? Like we thought about that a little bit, and basically, one obviously problematic thing is that even for NISC, I mean, compared to fault-tolerant regime, obviously, even for NISC, you need quite high fidelities to get anything of use, right? And you need to, like, for fault tolerance, well, you hit the threshold, and then, well, hopefully you do away with zero error effectively. But for NISC, you need to scale up your fidelity to get more reliable results for more qubits, right? So you need to scale up your fidelity, or like you need to increase the number of zeros, let's say by a factor of whatever, by you need to add 4 zeros if you want to run something on the 100 qubit device, if your circuit is n squared deep, which is like would be probably a minimal estimate, and on top of 3 zeros that you, or 3 nines, I'm sorry, like for infidelity zeros. So that's quite a challenge, and that basically there are two questions here. One is how can we maybe shift this challenge from the coherence times to maybe to the classical domain? And for instance, Nick suggested that well, maybe by some randomizing techniques we can shift all the error to the depolarizing channel, and then we can just post-select on everything. But that would then we will have whatever the corresponding scaling in the sampling that will also blow up. Well, we were talking about exponential, but it's probably not really exponential. It's like probably like n squared. So that's maybe that's something. Also something. Nick, would you insist it's exponential?
I think Nick might have just left, but I would say that it would be exponential in the system size divided by your T1, right? Because if you, I mean, it's basically exponential in the number of gates that you have to make divided by your T1. It's usually the cost, because that's kind of like the final circuit fidelity that you have is equal to the error rate to the power of the error rate per gate to the power of the number of gates. So if I fix the error rate,
that's what I would think. But then if you think about it, like if you're talking about really low error rates, the exponential would expand. You will have something that is close to 1 to the exponential of n, let's say, whatever, m. And then that thing would be like 1 minus m times the infidelity, rather than you see. So maybe it's not exactly exponential if you're operating in a low infidelity regime. If you're operating in high infidelity regime, it will be exponential.
I mean, I guess the point is that if you have an exponential but you're low within the exponential regime, then you wind up being linear.
Yeah, exactly. I mean, that's what I'm saying. Yeah.
Yeah, but I guess the thing is that that's only true when basically the number of gates you have divided by the error rate is equal to 1, and so then you'll need the number of, if I have a circuit that's on 100 qubits with depth 100, or if it's on 100 qubits with depth n squared, then I need to have that's 10 to the 6 gates, so I need to have 10 to the minus 6 error rates before that approximation becomes valid.
Basically, yeah. You need that anyway.
Guys, thinking too much about the gate errors may be problematic here, because if you're thinking about like parameterizing directly like your unitaries, and your unitaries are reproducible, even if you have like a coherent error like in itself, which is like reducing your randomized benchmarking performance in an ansatz, as long as you're producing the same pure state, you're going to be fine in terms of like doing minimization. It can be tricky if you then have to transfer like the ansatz between devices which have like different coherent errors. But in and out of itself, like the numbers exactly we get and the exponential decay we imagine is for assuming depolarizing channel, while we know large part of the noise is actually coherent errors like from crosstalks, which are reproducible given a set of controls, like on a device like a Sycamore.
I think the problem we have though, Pierre-Luc, is that a lot of the error that we have, biggest problem, one of the big problems we have maybe then is device instability, right? Because if the problem is that I go on, it's not like transferring the circuit between the different devices, but transferring the circuit between the same device on different days.
I agree. Like 1/f is probably there also. Like it's probably part of the trade-off also, like on the size of the system which can scale, because like those states will drift at some point. So like chemistry is difficult because of the huge number of measurements we have to do. Condensed matter, like uniform condensed matter systems, like are a bit simpler in the sense that like it's easier to use like a few reference, like few orbital frames, and like do those measurements there.
Yeah. But I guess I mean sorry, Bill.
But the media of them also.
Actually, I didn't. Yeah, I mean, I don't know, like how we're doing on time. There was one more thing I wanted to mention from our discussion, and basically that's yeah. Okay,
yeah,
so like it's like a social / human ingenuity aspect here, and that is like okay, if we need like 6 nines, right, or like 8 nines. Like who would be the experimentalist that would be convinced to do that instead of fault tolerance, right? And like the best thing we came up with was that, well, you know what? I mean, even if people will be working on fault tolerance mostly, and like they would be seeing, okay, well, that's where the future lies. But then, okay, we already hit, let's say, 4 nines or 5 nines, and we start working on fault tolerance. Fault tolerance will be building up pretty slow, and it will be ending up in quite slow circuits. So maybe maybe still part of the community will be interested in maybe doing some kind of shorter, quicker circuits, but that are facilitated by higher fidelities. That could be a possibility, but that would like really require some a lot of ingenuity invested in hardware. Instead of for some reason, instead of working on already a fault tolerance that is just available.
For simulation, the requirements for fault tolerance are less heavy than say Shor. Like for sure, we need like n bits of precision, and like that scales with the size of the problem. For chemistry, we need floating point accuracy for most interesting problem, and then that kind of fixes the amount of fault tolerance we need to input in the systems.
Did we have
like the register
one
size and phase
breakout?
estimation for chemistry is always the same size, independent of the problem.
Did we have one more breakout group that hadn't checked back in yet? I'd like to make time for them if we did.
No, everyone's back in the main. Everyone's back in the main group. Oh, you're saying there should be one more breakout
Yeah,
group?
I thought there were four sessions maybe. Did someone else from that fourth group want to chime in with some of what they came up with? Oh,
You're muted, Steven. Steven, you're muted.
So, sorry. Okay, so I'm from Breakout Group 2, and we didn't really choose a discussion leader, but I did want to point out some of the ideas that at least I said there, and then other people could say something. It strikes me that what's significant is, the quantum supremacy came in these random unitary circuits, and that if you look at the generic chemistry things, the classical calculations are really very good, and you have to sort of go, if you're looking for the near-term outlook, you want to get closer to the regime where we've already seen that the quantum computers can be classical, and so that's how you need your problems to be transformed to be closer to, say, something like random unitaries. It sort of pushes you in the direction of time evolution. You want to somehow get rid of the wide range of energy scales, because that, some, big term from the nucleus can really slow down your time evolution, say, without generating much entanglement. So, that's the sort of direction that you're most likely to see a real, effect. If you can, it means a lot of classical work to transform your system into something that's in that direction.
So would you say then that you're looking at it's a scale problem, that if we have too many different energy scales in the system, then classical computers or classical programs do very well, but if we have a highly degenerate system with a bunch of, all the gaps are suddenly the same, then this is where quantum computer will find advantage.
Right. So the quantum chemists know how to deal with a wide range of energy scales.
Mhm.
Don't cause so much of a problem. They know how to deal with lots of basis functions to a certain extent, although that's still a challenge. There's these various things, and but if you look at where things get really hard, it's when you sort of reduced to sort of the strongly correlated orbitals, the valence orbitals, very strongly interacting, generates lots of entanglement potentially if there's excited states and time evolution that can hurt things like tensor networks. That's a regime where there's sort of more opportunity.
Mm-hmm.
I agree to that. I mean, that's basically just to follow. That's why I mentioned heavy elements. So F elements is a pointing case for that. I mean, you have a lot of almost degenerate orbitals and a lot of strong correlation.
I'm curious if you touched on any other examples, especially where time evolution is something that we have some ideas of phenomena we'd like to study, where we're really the classical methods tend to break down.
Well, so let me just throw out one example. One of the classical methods for realistic F-electron systems, say, is dynamical mean field theory. And when you have these F-electron systems with lots of nearly degenerate orbitals, then this has a solver part of it that needs to do the hard work, the impurity solver. And those we don't have very good methods for. And it's it's got time in they maybe imaginary time evolution or real time evolution can be involved.
Okay. Did anyone have things that came up, in their groups or in this follow-up conversation that they feel like they want to get out on the floor before we close?
Maybe one thing, Bill. I mean, you also brought out an interesting point on community. I mean, also thinking of what Detlef said. I mean, situation when the DFT became so important. Coming back to your point and say, okay, once we've solved things, I mean, what was really pivotal for the DFT is that a lot of people started solving different problems in very much the same way, because chemistry is very broad. So there's lots of different small problems you want to solve, because I mean there's zillions of different materials people are working on, and I think that would be a challenge. Once you have something working that can solve something, how do you get hundreds of say computational chemists actually solving their problems of interest? I mean, first making them realize they can actually solve it now, and then actually organizing that they get access. I mean, and that they can run stuff.
Yeah, I certainly think it's a great success of the DFT community that I can download some incredibly complicated code and run it and get good answers for a real system in a few hours.
Yeah, but it took 30 years before you were able to do that, right?
Yeah. And the breakthrough was, as you said, that was already in the 90s. But I mean, it took a while before people actually, I mean, the bench chemists could actually use it in an easy way. But I mean, but I think that is something, I mean, if we say, okay, we solved it, I mean, that's still something to pay attention to.
Well, DFT sort of won the lottery. Walter Cohn didn't think it was going to work nearly so well when he worked on it. The other, this breadth of quantum chemistry also says that there's room for niche items. And I would be very excited for, a quantum computer that could solve any niche area better than the classical algorithms. I think that would be extremely exciting. DFT is is quite a goal to shoot for, but.
Yeah, but you're saying it's in the transition metal, F metal area. There's potential, so to say. Is that what I'm understanding? I thought that was an interesting twist, because I would not have picked that. I would have picked something really light.
Has pair condensation been observed in fermionic cold atoms yet?
May I have a comment?
The pair condensation in fermionic cold atoms.
What I'm saying is that may I have a comment?
Yeah, sorry. Yeah. Oh, please go.
So I just one comment that listening to what Steve said, but unfortunately the connection is always got broken, so I had to reconnect several times. So what we also do that with these classical algorithms like these tensor network states or DMRG, then we also do when we do the time evolution, we also optimize the basis. So that, as Steve said, that we have this different range of correlations. So there is this weak and strong correlations, and of course you need different basis sets. What we do now, we optimize this range entropy or other quantum information quantities, and not just the MPS manifold, but we also optimize the Grassmann manifold so that we also rotate the basis, so that we do these pairwise rotations. And this means that if you do the time evolution, then the entanglement that piles up because you generate more and more correlations. This is strictly connected to a given basis that you used at the beginning of your calculations. But now what we do a few time steps, and then we optimize the basis so that we lower the entropy. Then we go again for a few time steps, and then we optimize it again so that we can go much longer time scales than before just by optimizing the basis. And this is also connected to this relativistic case that we are doing this TCC, this tailored couple cluster on the relativistic domain as well, so that now it's generalized for not just the quantum chemistry, but for this relativistic one as well. And doing the same tricks, we got some basis from the chemist colleagues. So I'm not a chemist, so I'm just a fool in chemistry. But my interface is that I'm getting this information from the quantum chemistry colleagues, and then we do the mode optimization. So we again re-optimize the modes, so that just changing, let's say, the potential, just changing the hash, then for each point we re-optimize the basis based on these entropy considerations. So that this is how we deal with these different ranges of correlation. So that depends on whether you have a weakly correlated or a strongly correlated system in a given, or whether you have an avoided crossings or there is a lot of degenerate states. You can do this every time and every point in the hash, and that's actually it's far more stable. So I'm not saying that the classical algorithm is going to be the future, but I'm saying that there is a lot of potential still in these algorithms to improve step by step. And it's also by parallelizations that if you do all these things and together with these modern technologies that you have millions of cores on these GPUs and others, especially with these mode optimizations, we do all these with low bond dimensions in this very cheap DMRG or TNS calculations and do hundreds or thousands of sweeps. But this you can do. So it's a real question that if you find the optimal or quasi-optimal basis, you can really recover the real physical correlations, and that's independent of the representation, so in how you represent your quantum system, because there's also an artificial entanglement that the model gets into you. So basically, I think you have to combine all these things, and that's also directions what Steve is also mentioned, these wavelets and others. So it's basically, I think there is a lot of room. So actually, I don't see that if it would be a very interesting question that if you have the optimal representation of your quantum state for a given parameter set, then how far you can push it with classical computers. That's when quantum computers are really needed.
I think maybe we can expect that there will be a tug of war over that line when we finally feel like we've gotten there, as we saw with the random circuits. It looks like we're about out of time for our discussion now, but I really encourage everyone, if there's things that you didn't get to say or questions that you didn't get to ask, or just folks you'd like to talk to, reach out, through the Slack or to each other, and find some time to take advantage of the Wonder coffee hour spaces. And I know I would love to chat with more of you or all of you for some more time. Yeah, thanks for discussing today.
Thank you.
And thanks for a
cool discussion.
Notice, Bill. That's very great.
I want to say something that I heard from Matthias Troyer last year. He said maybe the only reason for building a quantum computer is to make classical computers better, and then we can throw them away. He said that last year in Veldhoven.
Yeah, well, then there's a statement about wanting to go to quantum computing that can be realized on 0 qubits, right? Which is Scott Anderson. It's another great statement.
We are being recorded right now, by the way. Probably unlike Troyer at that point.
Maybe we can end the recording with a round of applause for the organizers.
Bye, everyone.